So, today we start our discussion about central orbit. Central forces is a family of force field which has the following property. So, let us assume there is a particular type a force which is pointing towards this particular fixed point or pointing away from this particular fixed point. But let us say there is a force field with the origin O and there is a particle there are some particles moving in this system. Now, if the force on this particle wherever it is, does not matter if it is here or here or here or here, if the force is always pointing towards this fixed point or let us say from here, or if it is pointing out of this fixed point, that is also a valid central field. So, these are called the central forces. Now, central forces essentially means that it should always point towards or point away from a force field on a fixed point. That means, essentially it will work along the origin, along a line joining the origin and the object in question. So, if this is the point mass in question, then it will be the force will be along this. If this point mass is in question, then the force will be along this line. If this one is in question, so it will be along this line. If this one is in question, then it will be along that line. Could be attractive, could be repulsive, but it will always be along the line joining this point mass m with this origin O. Okay. Now, also the magnitude of the force is a function of this distance only. It does not matter if this particle is here or maintaining the same distance if it is here, the magnitude of the force on this particular particular mass point m will always be 1 along the line m to O, and 2 F will be the magnitude of the force will be proportional to or will be a function of r. Okay. So, these two properties, if a certain force has these two properties, then this is called a central force. Now, there is a very special class of property which is associated with the motion of a particle in a central force field, and this class of properties, first of all, central force field by nature is a conservative field. Okay. Secondly, it will be shown later on that if a particle is moving under the action of a central force field and if there is no other forces acting on this particle at the time of this motion, then the total, or rather I will just write angular momentum, the momentum is conserved. So, conservative force field, the first point essentially means E is equal to a constant, total energy of the force field is a constant. Now, angular momentum is conserved, that essentially means L is equal to constant. We write L for the angular momentum vector. Please understand that angular momentum is not a scalar. Energy is a scalar quantity. So, energy is constant means E as a number, as a number which represents the total energy is constant. But angular momentum conservation essentially means L as a vector is a constant. That means, it is not only the magnitude of that vector, but also the direction of that particular vector in space is a constant. Okay. And Number 3 is motion is planar. So, that means the motion of this particle m, for example, if it is due to this central force where the origin of the central force is O, let us say. So, if the motion of this particle is due to this central force alone, please remember if there is any other force acting on this particle at the same time, which is also possible. So, then we cannot comment on this motion, and this 3 sets of properties will not be valid. Okay. But if the force acting on this particle is only the central force, then we can safely say that the motion will be confined to a plane. Okay. Let us say the plane of this board. Okay. And these 3 properties can be proved. We will prove 2 of those properties in near future once we learn some of the required mathematical techniques. Energy conservation can also be proved very easily. Okay. So, let us give some examples. Very common, and we all know about it. Gravitational attraction is a central force. If we have 2 point masses, let us say, okay, yeah. So, let us say 2 extended mass bodies, I mean masses. So, the gravitational attraction between these 2 masses are always pointing along the line joining the center of forces, center of masses of these two bodies. Similarly, we can also take another very common example, that is Coulomb attraction or repulsion. So, or let's write it not as Coulomb attraction or repulsion, we will write it as electrostatic force, which is also an example of central force. And number 3 is another example is the spring force. Spring force is the force which let us say we have a spring mass system and it is oscillating only in the influence of the spring force, then we have simple harmonic motion, okay, which is also so the spring force we will see very soon that the spring force is also a special type of central force. So, these are the 3 very common examples. We are all familiar with gravitational, electrostatic and spring force, and all these 3 are central forces. So, we first started by defining, we have defined central forces by these 2 parameters. When the force, so the force has to be along a straight line joining a force center and the mass point, and the magnitude of the force is a function of the distance alone. Then we have given some properties. Okay. So, these properties we will prove systematically one by one in near future, and then we have given some examples. Now, as we see that okay, we do not know a priori at this point, but you have to trust me that we know in advance that motion is planar. Now, as the motion is planar, there is no reason that we, so if a point mass is like moving on a particular plane, how many coordinates do we need to describe it? We need 2 coordinates. In general, in Cartesian coordinate system or spherical polar coordinate system, they deal with 3 parameters. Let us say if it is Cartesian, then we have x, y and z. If it is plane polar coordinate system, then we have r, we have theta and we have phi. Okay. So, in either case we have 3 coordinate systems, but in this particular case, because the motion is a planar motion, we can bring it down to a 2 coordinate system and we can just work with plane polar coordinates. So, let us start our discussions, little bit of details about plane polar coordinates, and then we will come back and prove this two properties of central force one by one. Okay. Now, so let us say we have a Cartesian coordinate system x and y, and a particle is moving in some path in this coordinate system. So, if this is the position vector r of the particle at time t, and if this one is the position vector r plus dr in time t plus dt, then okay, so we can always express this r as a coordinate point x y, and express this one as a coordinate point which can be given as x plus delta x and y plus delta y. So, this is how we represent the motion of a particle or trajectory of a particle in x y coordinate system. Now, what we can do is essentially we can introduce a new coordinate system which is called the plane polar coordinate system, which will also have two parameters, but instead of x and y we will call them r and theta. So, probably you are familiar with it, but still let me go a little bit into the details of this. So, let us say instead of writing r in terms of x and y, we are writing it in terms of r and theta, r being the vector, okay, and this is the vector r plus delta r, which is given as x plus delta x plus y plus delta y, and we instead of writing it x and x plus delta x, we just write it as r plus delta r and theta plus delta theta. What is r and theta? R being the distance from this origin to this particular point, and theta being the angle it makes with the positive x direction. So, we have r, which is radial distance from origin, and we have theta, which is angle between the vector r and positive x axis. Okay. So, r plus delta r will be this distance, r is simply this length, r plus delta r is this length, theta is this, and this angle has to be delta theta. Okay. So, it's not so nicely written. So, now we have defined the parameters. Now, if you recall, in Cartesian coordinate system, we have the unit vectors I cap and j cap, right. Now, in this case also, if we are moving into plane polar coordinate systems and we have to write vector equations, so we need to have unit vectors, and so that means we have to define two unit vectors. One is along one is for r and one is for theta. Now, it so happens that writing the vector unit vector along r is trivial, because the direction will be the radial direction, which will be pointing outward from this origin. Okay. So, we call this like we have I and j. So, let us say when we have x y in Cartesian coordinate system, we have equivalently r theta in polar coordinate system. When we have I cap j cap in Cartesian coordinate systems, we equivalently have r cap and theta cap in polar coordinate systems. So, r cap being the unit vector along r and theta cap being the unit vector along theta. So, r cap is defined as the radical. So, essentially the unit vectors are, we know that by definition unit vectors are vectors of unit length pointing to a particular direction. So, in this case r cap points towards the radially outward direction, and theta points to a direction which is perpendicular to r cap. So, this is the direction of theta cap. Okay, fine. Now, what is so different about it? I mean, again, these are two unit vectors, and I cap and j cap are also two unit vectors. But the unique property of this is, here you please understand this, we can have different point location in a Cartesian coordinate systems expressed in terms of I cap and j cap. So, that I cap and j cap are fixed in space. We know that whichever point whichever vector we write, we always know that the I cap component means the component along x, and j cap component means it is the component along y. But here, as we move on along the trajectory of the particle, let us say when we go from r theta to r plus dr and theta plus d theta, the direction of these unit vectors also changes. So, at this point, if we try to, at this particular point, if we try to draw the unit vectors, we see that it is a new r cap. So, we just sorry, it's not nicely drawn. So, it has to be along this line. So, we call this r cap plus dr cap. That means, r cap is not a fixed direction, but it is also changing. Right now, let us say at time t it is given as r cap, in time t plus dt is given as r cap plus dr cap. Similarly, theta cap here is given as theta cap plus d theta cap. So, this is a very unique property for this thing, because if we take the time derivative of d I cap dt, which will be identically equal to 0 as d j cap dt, which is not the case here, because if we take time derivative of d r cap dt, it will be not equal to 0. Similarly, if we take time derivative of d theta cap dt, it will not be equal to 0. Okay. So, when we are finally, we have to, so to write the equation of motion of any object in a plane polar coordinate system, what we need essentially is we need first r, the position vector, then we have to define v, which is r dot, and then we have to define acceleration, which is v dot. So, it will be essentially r double dot. So, I hope you remember that dot essentially means d dt, and double dot is essentially double dot means d2 dt2. So, this is the first time derivative, second time derivative. Now, when we compute this r dot and r double dot in the plane polar coordinate representation, we also have to take into account that the radial the unit vectors along r and theta is also changing with time. So, there will be additional term coming in here. Okay. So, our job is to find out this variation in r cap and theta cap, then we can easily write the this one, the expression for velocity and acceleration. Now, if we draw these two unit vectors, or rather 1, 2, 3, 4 unit vectors separately, what do we see? Let us say this is our unit vector r cap, and this is our new unit vector r cap plus dr cap, where theta is this angle. Similarly, if we draw theta cap, please remember that theta cap is perpendicular to r cap, and theta cap plus d theta cap is perpendicular to r cap plus dr cap. Okay. So, if we draw this, my theta cap will be in this direction. Let us say I am shifting this vector to here and this vector next to it. So, this is your theta cap plus d theta cap. Okay. So, this is your theta cap plus d theta cap. So, the angle between them is d theta once again. Sorry, it is not theta, but the angle is d theta. Okay. Now, please try to follow this picture diagram now. We have a change in, this is given in time t and this is given in time t plus delta t. Similarly, this is given in time t, this is given in time t plus delta t. Okay. So, we have to write an expression for this dr cap, which is the change in this unit vector along r in time delta t. Okay. So, if we do that, we see dr cap is r cap delta theta, which is this distance. So, essentially it is r d theta. R cap is the unit vector, the length of this unit vector. Okay. So, this is 1, because the length of the unit vector is always 1. Okay. So, this is d theta, but there is a vector direction which is, so this change dr is in a direction which is perpendicular to r in the limiting case when delta t becomes 0. So, in the limiting case when delta t becomes 0, d theta also becomes 0, and r cap and r cap plus dr cap, they almost fall on each other. So, that means dr cap is a direction pointing perpendicular to r cap, which is the direction of theta cap. Okay. So, dr cap is nothing but delta theta theta cap. Okay. So, if we now take the limit delta theta goes to 0, this expression is nothing but dr cap d theta is equal to theta cap. Similarly, if we look into this carefully, here again the change in theta cap is given by d theta cap, which is d theta cap equal to delta theta times theta cap, length of theta cap, which is once again we will put 1. Okay. So, we are just putting 1 here, and it is a direction which is perpendicular to theta cap in this clockwise direction. Okay. So, please remember, sorry, anti-clockwise direction. So, this is the anti-clockwise direction of motion, this is the clockwise direction of motion, and anti-clockwise direction when theta cap changes in this direction, this essentially means it is changing along minus r cap direction. Okay. So, we have to put a vector sign minus r cap. Once again, if we explore the limit when delta t goes to 0, that means delta theta, okay, so this is theta, delta theta also goes to 0, we essentially get d theta cap d theta is equal to minus r cap. So, this is one relation and this is another relation, right. Okay. So, we have these two relations. Now, we will see how to get the expression for V and A using these two relations. And also please note that as if we move along this radial direction, neither of r cap nor theta cap does not change, because if we go from this point to this point, the radial vector is always pointing outwards, so that r cap is not changing. So, and if r cap is not changing, theta cap is always perpendicular to r cap, that is also not changing. So, we like these two relations here, we can also write, I will just write it together once again. So, we immediately see that d theta cap d r is equal to 0 is equal to d r cap d r. So, they do not change, the direction of r cap and theta cap does not change with changing r. But when it comes to theta, we have d equal to theta cap and d theta cap d theta is equal to minus r cap. So, these four relations we have to keep at hand. Now, if we start with r is equal to r cap, because r is a vector direction, r is a vector. So, there is a magnitude which is this length r, and there is a vector direction pointing outwards along r is r cap. So, r is simply this. So, V is equal to r dot is equal to r dot r cap plus r cap dot, which essentially means d dt of r cap. So, we will just write d dt of r cap. So, what we will do is we will just do a substitution here, r dot r cap plus r d theta of r cap d theta dt. So, this is a just we substituted the derivative d dt as d theta dt and d d theta. If we now perform this from this relation, this is nothing but theta cap. So, this is r dot r cap plus r theta dot theta cap, and this is nothing but theta dot. Okay. So, we replace this by theta dot, rearrange to give you this. So, this is the velocity expression. So, we get the velocity expression for the spherical plane polar coordinate system as this. We will write it again, r dot r cap plus r theta dot theta cap. Now, we take A, which is equal to, sorry, this is a vector here, V dot, which will be equal to r double dot. Okay. So, it will be r double dot r cap plus r dot r cap dot plus r dot theta cap plus r theta double dot theta cap plus r theta dot theta cap dot. Okay. So, we have 1, 2, 3, 4, 5 terms in this derivative. Okay. Can we? So, there is a theta cap which is not visible here. So, I will just write this term here. Theta cap dot. Okay. Now, I am leaving it to you to as an exercise to simplify this. We just like previous case, we have to replace this r cap dot as dd. We have to substitute for d dt is d d theta d theta dt. So, it will be theta dot d r cap d theta, and essentially what we will get is r double dot minus r theta dot square r cap equal plus So, this will be the final expression for A. So, we have one radial component and one transverse component.